Hello everyone, let's take a look at our next problem. If a cannon is pointed straight at a monkey in a tree, and the monkey lets go and falls towards the ground at the same instant the cannon is fired, will the monkey be hit? Describe any assumptions you make. So I happen to know the answer to this one already because I've actually seen it done in an experiment, not with a monkey. And the answer is yes, the object will be hit, or the falling object will be hit by the projectile. I saw this demonstration in a physics class a long time ago. And I suppose we'll just work out, all the kinematic formulas and so on. But let's also draw a picture of what's going on. So suppose we have an object suspended at a point here, which is a height h off of the ground. And we have our cannon here, which is aimed directly at the object. And we'll also say that the distance here, let's call this L. So the idea is that a projectile is fired such that its initial trajectory is directly at this object, but the instant that it's fired, the object is also released from its fixed position and it'll fall under the effects of gravity. But the same thing will happen to the projectile. As soon as it's fired, it will also follow a parabolic trajectory because of the influence of gravity. And what I want to show is I want to set up the kinematic equations here and show that the vertical position of the cannonball when it travels a horizontal distance of L will be equal to the vertical position of the monkey. And if they have the same vertical position and horizontal position at any point in time, this means the monkey's been hit by the cannonball. Okay. So what's the best way to do this? I'll start with the monkey first because the kinematic equations will be a little bit more straightforward. So the position of the monkey I'll denote by ym. This is going to be a function of t, and it'll be equal to the initial position h minus g t squared over 2, where g is the gravitational constant. Let me make sure that's correct. The volume at any point in time, or the velocity downwards at any point in time will be negative gt. It gains velocity at a rate g. So we integrate that and we get negative g t squared over 2. Yeah, okay. The cannonball, let's say, I'm also going to say that in terms of my x coordinates, the initial location of the cannonball corresponds to x equals 0 and y equals 0. So the origin, we'll say that where the cannon is, that's the origin. So this is correct because the monkey starts above the origin. Well, it doesn't have to, right? I mean, h could be negative. Everything here will work out. If the monkey starts, if the cannon is up on a hill that's taller than the tree, this will all still work out. So I'll write now the x position of the cannonball. So I will assume that cannonball is fired with a speed equal to v. So I don't really care how long that vector is, but we'll need to get the x and y components of that vector correct. So we're going to assume, I mean, this is not really an assumption. The cannonball comes out with some velocity. We are assuming that there's no air resistance, meaning that the horizontal component of the cannonball's velocity will be a constant. The only force acting on the cannonball after it's fired will be gravity, which is downward. So the horizontal speed of the cannonball will be v times, if I call this angle theta, it'll be v times cosine theta. Now I'm going to multiply this by t, because if this is the horizontal speed of the cannonball, then the position is whatever the speed is times t, because we're assuming the speed is a constant, the horizontal component at least. But we know cosine theta. Cosine theta is L over the length of this hypotenuse, L squared plus H squared square root. Just make sure that's correct. Yep. Okay. And the vertical position as a function of time. Well, let's write the vertical speed as a function of time too. So the derivative, well, this will be v times sine theta minus gt, right? So this is the initial vertical component of the cannonball speed. And as time goes by, gravity reduces that linearly. Okay, so this implies that the position, so I'm not writing the derivative anymore, but the position is going to be the integral of this, v sine theta t minus g t squared over 2. And again, we know what sine theta is here. It's going to be h divided by L squared plus h squared times t minus g t squared over 2. Okay, so what do I have here? I have, I have nothing. Come back. I have the position of the monkey as a function of time, and the position of the cannonball, both its horizontal and vertical coordinates, as a function of time. So the first thing I want to do is I want to find at what time is the horizontal position of the cannonball equal to capital L, because that's when the cannonball is passing through this vertical axis. Once I have that value of t, let's call that capital T, I want to substitute that into the vertical position of the monkey and the cannonball and see if those two things are equal. Okay, so capital T is defined as being, it's V L capital T divided by L squared plus H squared square root, and I want this to be equal to capital L. So I want to solve for capital T when this horizontal position is equal to capital L. So this gives me T is equal to L squared plus H squared under square root divided by V. Okay, good. And now the position of the monkey at time capital T is H minus G over 2 times capital T squared. Is that the right formula? Yep. So we've got L squared plus H squared over V squared. It's the position of the monkey at time capital T, the vertical position. And the vertical position of the cannonball at time capital T is VH capital T divided by L squared plus H squared under square root minus G over 2 capital T squared, and now we can substitute what capital T is. And we should see right away that these things are equal. I get a lot of cancellation on the left. This just turns into H minus whatever, G over 2 L squared plus H squared over V squared. And this is the same as the position of the monkey, right? Both of these expressions here are the same, meaning that the cannonball does hit the monkey when it crosses that vertical plane. Yeah, I think there's another approach to doing this question. If I remember the context of when I was shown this experiment, how long ago was that? 20 years ago. 20 years ago, this experiment was actually shown to me, and I believe it was in the context of changing the frame of reference in a physical system. I mean, so the way we did it here was kind of a lot more direct, really just computing the position of all relevant objects as a function of time and showing that they do occupy the same point in time or same point in space at some point in time. But there's another sort of clever way of doing this by changing the frame of reference. I don't remember what the details were of that. Maybe I'll think about this in the back of my mind over some time and maybe come back and demonstrate what that looks like. But overall, this is kind of a nice problem. Thanks for watching.